In this presentation, we will explain our solution approach, which secured the 5th place in the game playing strength of Monte-Carlo 3 search variants competition organized on Kaggle. Let's take a look at the content of our presentation. First of all, we will introduce ourselves and share our experiences in the background section. Next, we will provide an overview of our solution approach, which integrates Anil's pipeline and my pipeline. A critical part of our process was feature selection and engineering. We will give more details about our feature selection and engineering processes of our pipelines. And also, we will talk about our training methods. We preferred to use various training techniques to reach better results. We are going to continue with the important and interesting findings that we have faced during the competition. Finally, we will conclude the presentation by showing a simplified version of our solution, which is based on Anil's pipeline. Background, my name is Sercan. I have a bachelor science degree in statistics from Yıldız Technical University. I'm working as a data scientist at Garanti BBVA nowadays. And I have 3 years of experience in that field. And I have mostly worked on supervised learning tasks so far. Anil, you can continue.
Okay, and I'm Anil. I hold a bachelor's in mechatronics and master's degree in computer engineering. I'm in the field for like 4 years, and currently I work as a senior data scientist. And I have an experience in tabular data, time series problems, NLP, and reinforcement learning.
Okay, summary. We can see the summary of our solution approach in this slide. First, we trained a diverse set of models, including CatBoost, LightGBM, and neural networks. This combination allowed us to leverage the strengths of different modeling techniques to achieve robust predictions. For validation, we used both group k-fold and stratified k-fold approaches, and these strategies unsecured that our models generalized well by maintaining the grouping and stratification properties of the data. Through feature analysis, we identified that the most important predictors were the advantage of player 1 and player 2, along with agent component features. These features played as a crucial role in driving the performance of our models. Our entire solution was implemented in Python. And lastly, while training times varied across different approaches, our final submission was highly efficient, taking approximately 2 hours to run. This balance of accuracy and computational efficiency was key to our solution. Feature selection and engineering processes was crucial in our both pipelines. Now Anil is going to tell about his pipeline.
Okay, so I actually didn't go overkill like doing exhaustive feature engineering, etc. I just came up with a few simple things. I split the agent string into components as new features and created adjusted versions of the advantage values. It basically splits draw effect to both players equally and recalculates the advantage based on the completed games. And finally, I swapped or inverse calculated the position related features to get an augmentation like effect, and it helped a lot. And this is the feature importance plot of my models. As we can see, my models use the component features, augmented features, and the adjusted values that I mentioned a lot. They're at the top in the importance plot. Yeah, that's it.
And now I will tell you about my pipeline. For GBDT models, including CatBoost and LightGBM, we extracted TF-IDF components from several key text sources like Agent 1, Agent 2, English rules, and LUD rules. To ensure we retained the most impactful features, we applied feature selection to these TF-IDF components using CatBoost's built-in feature selection tool. This helped streamline the model link process and improve model performance. When it came to the deep tables approach, I applied specific preprocessing steps to optimize its performance. Numerical features were scaled using a min-max scaler to ensure consistency in their range. Additionally, agent components were manually split for better granularity, and rule-based features were removed as part of our feature engineering process. Uh, to sum up, this combination of preprocessing, feature selection, and tailored pipelines for different models formed the foundation of my solution pipeline. Uh, My GBDT pipeline consists of two base and two meta model training. In these charts, we can see the average feature importances of my base models, which were like GBM and CatBoost. Initially, we observed that agent features had the highest importance in our early experiments. Because of that, we decided to extract some components from these features to get more accurate predictions. It worked well for both models and carried us on the leaderboard during the competition. In these two charts, we can see the average feature importances of my meta models, which were stacked with out-of-fault predictions of my base models that we saw in the previous slide. Out-of-fault predictions took the top 10 place for both models and improved our models' accuracy. And
Yeah,
yeah,
these are the features that caught our eyes during the competition. These are the advantage values. We can see a linear correlation with the advantage of the first player with our target, and the inverse kind with the second player. We can move on. And this is the exploration constant of the agents. There is a positive correlation with the first agent having a bigger constant, but it harms the second one, as we can see. We can move on. And this is the balance feature of the games. And we can see that when a game is being ultimately balanced, the game outcome also converges to zero sum as expected. And we actually see that effect after like the 70% of a balance in the games. Yeah, that's it.
thank you, Anil. And now I will continue with our training methods. This slide highlights the key aspects of the training methods that we utilized in our solution for both my pipeline and Anil's pipeline. For machine learning, we adopted gradient boosting decision trees as our primary approach, leveraging algorithms like LightGBM, CatBoost to achieve robust predictive performance. And for the deep learning side, we implemented diverse network architectures like DNNs, FMs, CINs, and IPNN to capture complex patterns and interactions in the data. And our final solution was centered around an ensembling approach, combining the strengths of these models to achieve better overall predictions. To optimize this ensemble, we carefully analyzed the cross-validation and leaderboard scores of each model, using them as a basis to adjust their weights and create a balanced and effective ensemble. We can see the final weights here for three separate approaches. This strategic blending was key to maximizing the accuracy of our final predictions. Let's continue with important and interesting findings that we have faced during the competition. Ensembling models and applying data augmentation were crucial in boosting performance. A significant factor was updating features like advantage player one during data augmentation to maintain consistency. We also observed that the sum of completion and provisioners should equal 1, except for the safe passage rule set. This inconsistency was confusing, especially applying data augmentation. However, considering the frequency of the data size, we have just ignored it during augmentation. Now I will continue with the simplified version of our solution, which bases on Anna's pipeline. Anna's Cat Boost, trained with augmented data, is our simplified model. As I said, it takes nearly 10 minutes to train and simplified model pipeline on our local machine. You can see the modeling and preprocessing flow here. We also added the leaderboard scores and also cross-validation scores here. And that's all. Thanks for listening.